Hello everybody, this is Mr. Casil. So, we're going to be diving into the notes for pre-calculus today. I want to remind you guys from where we left off before, we were just doing an algebraic proof and showing that 2 is equal to 2 by using what we knew about algebra, right? We were looking at patterns, looking at canceling things out, and so what we're going to do is that same idea but for trigonometry. And in order to do that effectively, you need to know what the rules are of trigonometry. So the beginning of this video is reviewing those rules. If you're in one of my periods who made it a little bit further when I was there, you can skip ahead in the video. Effective video learning involves rewinding, fast forwarding, pausing, and all those other details that you need. So a lot of these basic trig identities will be identities that should look familiar because you've already used a little bit of trigonometry. Here, we have the reciprocal identities. Reciprocal just means the flip of the fraction. And so our cosecant is 1 over sine, secant is 1 over cosine, sine is 1 over cosecant, and that does mean because it's 1 over cosecant, if you see that cosecant is in the bottom of your fraction, then you're dividing by a fraction. So multiply by its reciprocal. If you have cosecant on the bottom, you can simplify that, focusing on its identity, rewriting the same thing in an easier way by writing 1 over cosecant as sine. And you can do the same thing for cosine. 1 over secant rewritten is the same thing as just writing cosine. And you can see that that is incredibly efficient for trying to simplify and work with more complex trigonometric functions and expressions. Now, for tangent and cotangent, normally we see tangent as sine over cosine, which you can see right down here. And even though the textbook identifies it as a quotient identity, you're not going to need to memorize that it's a quotient identity. What you really need to focus on is that definition of its identity, that tangent is sine over cosine, which means if you reciprocate tangent and write it as 1 over cotangent, that does mean you're dividing by a fraction, and having 1 over cotangent, having 1 over cosine divided by sine, multiplied by the reciprocal, gives you sine over cosine. So you can actually represent that as an identity in multiple ways, either as rewriting tangent as 1 over cotangent, or if you see cotangent on the bottom of your fraction, simplifying that and just writing tangent on the top of your fraction. Same thing for cotangent. If you have tangent on the bottom, you can rewrite that so that you have cotangent on the top. Now, for a lot of the strategies we'll take in working with trigonometry, we sometimes will want to leave things in terms of tangent and cotangent, but most frequently, we'll actually want to break tangent and cotangent up into its parts and actually write it as the fraction of sine over cosine and cosine over sine. Now, a few more identities that will help us in using sine, cosine, and tangent is its cofunction identities. Think about kind of like in how we have sine and cosine, secant and cosecant, tangent and cotangent. Right, means together, and the identities about putting sine and cosine together come down to about how they're off by 90 degrees, or in radians, they're off by pi over 2 radians. So if you see cosine, you can write that in terms of sine by subtracting theta from 90 degrees. Same thing for cotangent to tangent. Same thing for cosine to sine. And that does mean, because secant and cosecant are the reciprocals of sine and cosine, if you take secant and subtract its angle from 90 degrees, that is the equivalent of cosecant. Same thing for tangent to cotangent, right? Just like you can take cotangent and subtract its angle from 90 degrees and rewrite that as tangent, you can do that for cotangent by subtracting theta from 90 degrees. Cosecant and secant as well. And so it is a lot of writing that you see up here on the screen, but they're all rules that we can use in order to write something as a new identity. Maintaining its identity, but writing it in a new way. Now, some other rules that we can apply are even and odd identities. Remember, even as a graph means that one side of the graph is the same as the other side of the graph. So if you have an even graph, the left is going to be the same as the right. And so when we have our trigonometric functions, an even function means that when the left and the right are the same, like cosine, that if you have a negative value for cosine, it's the same as the positive value for cosine. So a negative angle for cosine is the same as a positive angle. You basically can ignore the negative in your parentheses. And its reciprocal is the same. Secant would also be even, so you can ignore the negative in the parentheses because you can rewrite that as a positive because it is the same. It maintains its identity. And so even, because it's the same on the left and the right, you can ignore the negative in those parentheses. Meanwhile, odd, because rather than it being a reflection over your y-axis, it's a rotation about the origin, when you have an odd function, the value that you have in the positive for sine is the same value when you're in that negative direction. So a positive x value has a positive y value, whereas you have the same value when you go left but down. So a positive x would have a positive y, but you'll have the same number, negative x and negative y. That's the reason that if you have a negative outside of your sign, that's the same thing as having a negative on the inside of your sign. The negative x is the same thing as having a negative y. And so you can take that negative inside of your theta and rewrite it as a negative on the outside of your sine function. That's going to be the same thing for secant. It's reciprocal. And then you might look at tangent and cotangent and wonder why they follow an odd identity. And the reason why is because of that tangent and cotangent's definition. Tangent is sine over cosine. So if we take that negative theta, tangent of negative theta is the same thing. Let me rewrite that theta there. That's really messy. Here you go. Tangent of negative theta is the same thing as the sine of negative theta divided by the cosine of negative theta. But what happens? Well, the cosine of negative theta is even. So when we rewrite the cosine of negative theta, that's just positive theta inside. That's cosine of positive theta. And so the reason why the whole tangent is negative is not because of the cosines change, it's because of the sines change, the fact that sine is an odd function. So when we rewrite this, that cosine of negative theta is still positive theta inside, but the sine function here has the negative taken out front. So we end up with a negative sine of theta divided by your cosine of theta. And because you have your sine and cosine, give myself a little bit of space here. And because you have your negative sine divided by a positive cosine, that's the same thing as just having your negative tangent. And so, because only the sine is odd, that ends up working out really well, so that your tangent basically follows the same rule as having sine being an odd function. And if you look at the graph, you'll notice that tangent's also an odd function that way. Now, we'll be able to continue and take a look at the other key identities involved with our work. The last and probably the most important is the Pythagorean identity. Now, I'll admit this is an absolutely terrible picture, but it's because I took this straight out of the text using my ancient laptop. When I looked online for other photos that would have better resolution, I really valued the text and the fact that it aligned these equal signs. And I'll talk about why here in a moment. But I really want to go into where this identity comes from. And it comes from, as you would guess, the Pythagorean theorem. You have a right triangle. And in your right triangle, when we're talking about the unit circle, you always have your hypotenuse as the radius coming from the center of your unit circle. So when you look at your coordinate grid, what you have then is your radius, and in your unit circle, the radius is always 1. But then you have your x and your y values, but because we're talking about the unit circle, your y values are sine of x, or I should say theta, if I'm being consistent, sine of theta. Your x values are cosine of theta. And if we apply the Pythagorean theorem here, you have your a squared plus b squared equal to c squared. Sine squared plus cosine squared equal to 1 squared, which of course is just 1. And this Pythagorean identity keeps showing up because we use right triangles to solve for distances like we did back in geometry and algebra 2, and because we have that connection of right triangles in our unit circle, we can have that connection help us solve for identities. 1 is a powerful number for identities because multiplying it by 1 keeps it the same. So where does these two equations come from? Well, they are looking at your Pythagorean identity, cosine squared plus sine squared is equal to 1, but we're rewriting that based off of where we want our value of 1. So if you notice, down here in this line, this is where our 1 is, and that's because in order to get from cosine squared plus sine squared equal to 1, we just divided everything by cosine. Cosine divided by itself is 1. Sine squared divided by cosine squared is tangent squared. 1 over cosine squared is our reciprocal identity. 1 over cosine squared is secant squared. And once again, that's something worth memorizing, because if we see a secant squared, we can write it as 1 plus tangent squared. If we have a tangent squared, you can imagine subtracting by 1 on both sides so that you can replace tangent squared with secant squared minus 1. There's lots of different ways these identities can be applied, because that's where the creative thinking comes into working with our identities and proving these identities. And then, of course, this last line right here, if you haven't already noticed, you would take your sine squared and divide it by sine squared to get 1. So cosine divided by sine gives you cotangent, and 1 divided by sine is that reciprocal cosecant. So each of these are just variations on that same Pythagorean identity. It's the same identity written 3 different ways. So for the rest of the video for now is just looking at a couple of examples of applying these identities. So our first one, we want to write sine of theta minus pi over 2 in terms of cosine. You can look at your notes right now and see your co-function identity. And you'll notice, and pause, if you haven't written down what we've just discussed, please go back and do so, rewind, pause, do what you need. Because you should look at your co-function identity and notice that this is equal to cosine only if the pi over 2 is first. And so what we need to do is we need to rewrite this so that our pi over 2 is first. And how can we do that? Well, we can do that by applying a clever way. We can basically multiply this by -1. That means we have our sine of negative times that theta and pi over 2 switched. And if you're not quite sure why we could do that or how we could do that, I want to bring you to thinking about distribution. If we multiply by this negative, by pi over 2, a negative times a positive is a negative, and a negative times a negative is a positive. what I just did in this one step was I also flipped the direction. So rather than having the pi over 2 second, I wrote it as the pi over 2 in the first place. That way we can clearly see its connection to our co-angle identity here. Our co-function identity, excuse me. But in order for us to really pull that off, we have this pesky negative that we introduced so that we could have it match our co-function identity. But that's where our even and odd identities come in. We know that the negative on an angle for sine is the same thing as writing the negative on the outside. So this is the same as a negative sine of pi over 2 over theta, pi over 2 minus theta. And now we can apply our co-function identity. The sine of pi over 2 minus theta is the same as cosine, and so we have our function in terms of cosine. It is equal to a negative cosine of theta. So, again, talking about how we got to this point, we started in the original function and made a connection with one of the rules we just covered. We made a connection with one of those rules that we're memorizing. We see this theta minus pi over 2 and said, wow, that looks a lot like the co-function identity. What do I need to do for it to be the co-function identity? I need that pi over 2 in front. So we did that step, put the pi over 2 in front with our negative, and then looked for our other connections, our other identities. That negative there is an even and odd identity. So we took that out in front, and that's where we could simplify it and write it in terms of cosine. Another example, simplifying the expression. This one's going to be fun. What do you notice? When you look at this function, what patterns do you see? Because I see that this here and this here have a sign in common. So we should factor that. So let's rewrite that with that sign factored out. So pulling a sine out of sine cubed means we have two signs left over. So we'll have sine of x times that sine squared left over. And then I'm adding on, pulling out a sign from here. What's left over is going to be cosine cubed. Oh, excuse me. How did that slip past my notice? That shouldn't be a cubed. That should be a squared. Let me fix that. So that should be a cosine squared. And honestly, what I just did was I noticed that sine squared and cosine squared is one of our identities. So when I looked at my notes that I wrote down earlier, I realized, oh, I made that mistake because we're really modeling those identities here. So we have sine squared and cosine squared left over, and our Pythagorean identity tells you that sine squared and cosine squared together is 1. And so rewriting that here, you have that sine squared that we factored out. So we have that sine of x right there, and what's left over is that sine squared plus cosine squared, which is 1. And anything times 1 is itself. So sine of x times 1 just leaves you with sine of x. And that is our simplified expression. All of this is just a fancy way of writing sine of x. Now, last example. This one's really exciting. We're going to simplify the expression, and sorry, this isn't the last example. There's one more after this, but this is a really fun one. We have the secant of x plus 1, the secant of x minus 1, all divided by sine squared of x. So, where do we start? What do we notice? Well, by now, you should feel comfortable with noticing the difference of squares. The difference of squares is having that first term the same in both spots, but the difference is you're adding and subtracting with each of those factors. And so, when we take care of this, when we multiply by the difference of squares, on the top, you'll have your secant squared of x minus 1, and that's all still divided by that sine squared of x. So, what do we do now? What we do now is we look for those patterns. This really looks like it should be a Pythagorean identity. So if you go and look back at your Pythagorean identities that you have written down in your notes, take a peek at it. I'll actually also scroll up here. If we take a look at our Pythagorean identity, that looks a lot like this, except our secant squared isn't by itself. Our secant squared is subtracted by 1. And so, with that in mind, if we had subtracted 1 on both sides, we know that secant squared minus 1 is the same as tangent squared. So we can make that substitution. We'll replace our secant squared minus 1 with our tangent squared. So, applying that here, I'll rewrite this as tangent squared minus 1 all divided by sine squared of x. Let me get rid of the minus 1 there and put the x in there. So we have tangent squared of x divided by the sine squared of x. So what do we do here? How can we simplify this a step further? Well, I'm going to look at this tangent squared of x and realize that if I want to simplify this, I'm going to rewrite this tangent in terms of sine and cosine, because that will help me identify what I can combine and what I can eliminate, what I can simplify with that sine squared of x. So, taking that next step, we'll write the tangent squared of x as sine of x. Let me keep using blue. I like that blue color. So, we'll rewrite that as sine squared of x divided by cosine squared of x, all divided by the sine squared of x. And I'm sure that every single one of you have noticed we're dividing by a fraction, and when we're dividing by a fraction, we want to rewrite it as multiplying by the reciprocal. And so we'll have our teal sine squared of x divided by cosine squared of x, and multiply by the reciprocal means this sine squared of x, even though it's on the bottom of our giant fraction, this is on the top of the bottom part of the fraction. So when I write it as a reciprocal, I'm going to write that it's 1 over the sine squared of x. And so, now that we've rewritten it as multiplying by the reciprocal, I hope you all notice that we can cancel out our sine squared of x's, meaning we're left with 1 over the cosine squared of x, and that is a reciprocal identity. 1 over cosine is the same thing as writing secant. So we have the secant squared of x as the simplification of this trig identity. If you're wondering, why didn't I leave it in terms of cosine? If I'm absolutely honest, it's because when we just say to simplify, generally, if we can avoid writing it as a fraction, it looks prettier, it's easier to read. And so simplifying this here to secant is just because that's easier to read. But sometimes you'll see in the directions it specifies simplify it in terms of sine and cosine, and if that was the case, I would have left it like this. So, last example, simplify the expression. We have cosine of x divided by 1 minus sine of x, subtracted by sine of x divided by cosine of x. Simplifying this expression, one of the things I notice is we're subtracting fractions, and really, we should probably get a common denominator. We should probably rewrite this in terms of one big fraction, which means I need to multiply this left side of the fraction by cosine over cosine. So I'm going to multiply this by cosine of x over cosine of x. And on this other side, I'm going to need to multiply by 1 minus the sine of x over 1 minus the sine of x. So, rewriting this now gets really exciting. Let me go ahead and actually bring it down to the next line so I can give myself plenty of room. So we'll have the cosine of x times the cosine of x, which is just the cosine of x squared. And that's all divided by the cosine of x times 1 minus the sine of x. And we're subtracting that by sine of x times 1 minus sine of x. So I'll go ahead and write that out. The sine of x times 1 minus the sine of x, all divided by the same denominator, the cosine of x, times 1 minus the sine of x. So let's do some simplification. I'm going to go ahead and actually subtract these two fractions together. Remember, the common denominator stays common, so we don't actually change the denominator. It's still just cosine of x times 1 minus the sine of x. But on the top now we have the cosine squared of x minus the sine of x times 1 minus the sine of x. So, once again, comes down to, what do I notice? Well, I have a cosine squared of x. I really feel like the cosine squared of x should be paired up with a sine squared somewhere, right? It feels like there should be a Pythagorean identity here somewhere. So I want to multiply by the sine of x and see if I can help make that happen, if I can use some creativity to massage this to get a Pythagorean identity. So distributing that sine of x, boom and boom. I want to make sure I don't forget my negatives because I have a negative sign right here. So a negative sign times a positive 1 means, bookkeeping is important, we have the cosine squared of x minus the sine of x, and then negative sign times a negative sign is a positive sine squared of x. And of course, that's all being divided by the cosine of x times 1 minus the sine of x. So, guess what, guys? We do have our Pythagorean identity. We have the cosine squared of x plus the sine squared of x. So we know that that is 1. So I can rewrite this and put the sine squared here in front, but if everyone's okay with it, I'm just going to write that this is the same thing as 1 minus that sine of x, all divided by cosine of x times 1 minus sine of x. And that's very satisfying because now we have the same thing on top and bottom. We now have a 1 minus sine of x on top and a 1 minus sine of x on bottom. That basically just fell in our lap. So those cancel out because anything divided by itself is 1. So what we have is just 1 over the cosine of x, which is the same thing as writing secant of x. So, ladies and gentlemen, thinking through what we took in those steps and where those steps came from, right? As I scroll back up to the very beginning, we saw we had subtraction with two different fractions, so getting a common denominator was the first step. I didn't know that 1 minus sine of x was going to cancel out in the end. I just was focused on getting that common denominator and then looking for a new pattern. And that's where the cosine of x came from. And because we knew our Pythagorean theorem, we knew that that identity for cosine of x should be paired with a sine squared of x. So that's what we focused on next. Notice, I never multiplied the bottom together. Why? Because I didn't see any patterns with cosine of x times 1 minus sine of x. This doesn't have a second power. So I wasn't paying attention or thinking about trying to get a Pythagorean identity on bottom. So I left those separate because it's easier to work with those factors than it is to work with those terms. It's easier to work with them as multipliers than multiplying them together and emphasizing the fact that they're being subtracted. So that's where that distribution on top was our priority, to get that Pythagorean identity. And when we got that Pythagorean identity, that's when we noticed a new pattern that our 1 minus sine of x's would cancel out, and we'd have a really convenient function ending with secant of x. So, ladies and gentlemen, thank you for sticking with me in this much longer video. It covers about 2 days worth of instruction. So for the rest of the period today, you're working on your homework and your practice. So I look forward to seeing you all soon. Hope you all have a lovely afternoon.